Hey kids, Charlie Abisso here. I'm back. We're back with some more good stuff, right? We got water class number 2. I'm trying to move my picture out of my way so I can do a good job for you. All right, mastering table G. Take it out, right? You got to have it. You cannot do this part of this class unless you have table G. You got to put your finger on it. You got to read the graphs, okay? You got to get it. Table G, called the solubility curves at standard pressure. Excuse me. How concentrated a solution is makes a difference, right? It doesn't matter what solution it is. Ammonia, HCl, hydrochloric acid, or even chocolate milk, salty water. How salty is it, all right? When you have salty water, what's the solute, what's the solvent? Whatever goes into the wet, that's the solute. The salt is the solute, the water is the solvent. For chocolate milk, which is which? Well, it depends on how you make it. If you make it with enough chocolate sauce, it could be either way, but really the chocolate sauce gets dissolved in the milk. The chocolate sauce is the solute, the milk would be the solvent. And what about ammonia? When you clean with ammonia, ammonia is dissolved in water. It's not 100% ammonia, that's almost poison. It's dissolved in water. Household ammonia, I think, is like 5 or 6%. It's plenty strong enough. You can't have 100% ammonia. So the ammonia would be the solute. Now, every solvent can only hold a certain amount of stuff. Depends on what that stuff is. It also depends on how much solvent you have, and also what's the temperature of the solvent. Usually, when the water, for instance, is cold, it will hold less than when it's hot. When it's hot, the water molecules are moving fast. Kind of they juggle a lot faster or juggle a lot more. But when the water molecules are moving slower, because the temperature's cold, it can juggle less. So there's a couple of factors. And we got table G to help us along. All right, table G is all about water, aqueous solutions. So these are all the answers. How much stuff fits in the solvent is called solubility. How much will dissolve into the solvent? Now, look at these pictures. Chocolate milk with the red fancy font, that's my chocolate milk, and here's my wife's chocolate milk. Look at it. I mean, you might drink it on a bad day, but it's much, much less chocolatey. Mine is more concentrated. Mine has more chocolate dissolved in the milk. Mine has more solute per unit volume, right? My wife's little squirt, right? She's worried about how much sugar you're going to get. Maybe you get a little hyper and start tapping too much. There's room in my wife's chocolate milk for a lot more chocolate, right? It's unsaturated. My chocolate milk, saturated, packed, chock full to the max. There's the most possible chocolate in the chocolate milk. My wife's chocolate milk, plenty of room for more chocolate, right? Maybe it's healthier. Who cares? You don't want to drink it anyway. Look at it. It's ugly. All right. Here's mine. This is the coolest table, right? Because it's like a spider web. It's so cool, right? There are 10 curves or lines on this graph. 10. It's confusing. Look at it. It's like a mess. You got to have little arrows to tell you which compound works for each line. It's a little messy in there, right? No, don't worry about it. We look at one line at a time. One line. The rest of them are just distraction. You don't look at them. One at a time. Don't get scared. Now, table G is called solubility curves at standard pressure. Now, standard pressure just means it's standard pressure, 101.3 kPa. You don't have to worry about it anymore. It's a normal. Now, the y-axis, it goes up and down. It says 100 grams of solute per 100 grams of water. Now, in my whole life, I never made a solution of 100 grams of water, right? It's 100 mLs. Change that right now, okay? We don't make solutions like that. The state does that right to drive you crazy. 100 mLs and 100 grams for water is the same thing, but 100 grams is confusing. Cross that right out. Fix it right now, right? One nice line. Cross it out. All right? Got that? Got that because we're moving ahead. On the bottom axis is temperature in degrees centigrade, right? And if you have to, it goes from 273 to 373 in Kelvin. It's the temperature. Now, how come it doesn't go below 0 and how come it doesn't go above 100? Think about it. This is aqueous solutions, right? And the reason is because water doesn't really go below 0 and stay a liquid, or above 100. Now, actually, with stuff dissolved in it, you break that rule a little bit, but it goes from 0 to 100. Now, how do we read this graph? How? First, you got to find the KCl line, right? My KCl line is right here. Let's see if I can point to it. KCl line. See my arrow? I don't know if you can see this arrow or not. KCl, right down here. It starts out at like 27, and it goes all the way up to about, I don't know, 55. How many grams of potassium chloride fit into 100 mLs of water at 10 degrees? I'm going to have to draw a picture on this graph so you can see, right? So I'm going to pick a nice color that you'll see, a nice blue. And at 10 degrees, here's 10 degrees down here. At 10 degrees, the KCl line is going to cross right here, right? That's where the dot is. So it's going to be 30 grams. 30 grams of KCl fits in 100 mLs of water at 10 degrees. Now, we'll do a different color. How many grams of SO2 fit in 100 mLs of water at 40 degrees? Well, let's find 40 degrees. 40 degrees is down here in red. Where the heck is this SO2 line? Oh, look, it's really close. So here's the place where we have to look. And what temperature is that? This one's a little tricky, right? It's in between, maybe 5 grams. Now, how about this one? We'll do one more color. I'm getting into this color stuff. Can you tell? We'll do a nice green. 100 mLs of water at 5 degrees, how many grams of ammonium chloride? So here we got to go look. 5 degrees. Now, where the heck is ammonium chloride? Ammonium chloride. We got to really look because it's very confusing. Ammonium chloride. Right here. Here's ammonium chloride. So we'll stroll all the way back right to here. Right? Let me get a good look at this one on my real graph. Ammonium chloride, and at 5 degrees, wow, it's really tight in there. At 5 degrees, it's really close, really close. All right, let's clear these pictures so we can see what we got. 30 grams, 5 grams, 32 grams. So let's see what we got. That doesn't make sense. 5 grams. SO2, yeah, 5 grams. Look at it down here. And those two are over here. They're both about the same. 35 and 40. No, something's wrong. That 40, 30 and 30, yeah, no, 30 and 32. We're good. This is all perfect. Okay? How do you use table G? You got to know what you're looking at. You got to know the temperature, and it will tell you how much stuff fits in. What else we got? Ready? Oh my gosh, there's so many here. How many lines are on this graph? 10. How many compounds? I can't read the question because my picture is blocking. How many compounds are on this graph? 10. How many lines go up? I'll give you a second. You count them. I'll drink some seltzer. Start low, go high. Trend. 7. 7 go up, 3 go down. Okay, now. Look at these compounds. This is a hard one, number 40 and 41. How many of these compounds are ionic compounds made with ions, and how many are molecular? Tricky business. 7 go up, 3 go down. 7 are ionic, 3 are molecular. The 7 that are ionic, more stuff fits into 100 mLs of water what's hotter than when it's colder. So the 7 that go up are all ionic, and the 3 that get lower are all molecular. So say something sensible about this, right? Molecular compound solubility in water decreases with higher temperature. The hotter it is, the less the molecular stuff fits in. You know why? Shakes up and turns to a gas and jumps out of solution. Now, the ionic compound solubility in water increases with higher temperature. Why? Because when the water moves faster, it juggles faster, it can hold more ions. Pretty cool. Pretty cool. You caught up? All right, here we go. How many lines can you look at a time? Just one, don't freak out. When something like Ki or NaCl, potassium iodide or sodium chloride goes into water, What particles end up in water? You shake some salt, right from your salt shaker, NaCl. What particles end up in the water? What do you think? Sodium chloride particles? No such thing. When it goes into water, what do? They turn into sodium ions and chloride ions. When an ionic compound dissolves in water, it comes apart into loose ions. Now, what about sugar? That's sucrose, C12H22O11, the white stuff you put on everything that's good. Sugar. Or carbon dioxide. Look, I got carbon dioxide in my seltzer. Carbon dioxide. What kind of particles go into the water when you dissolve sugar or carbon dioxide? Molecules. There's no ions and they don't come apart, right? They don't come apart. You get small molecules, they're invisible, but they're whole molecules. They're not ionic. This is easy. Yeah, math. It's easy. How many grams of ammonia fit into 100 mLs of water at 90 degrees? So I will look at 90 degrees, which is way over here, and slide up to ammonia, which is the second line, and it says 10 grams. 10 grams. Okay? This is a saturated solution. Think about it. I'm going to draw you a picture. Here's a solution that has exactly 10 mLs of solution that has NH3 aqueous in it. See that? If it's at 90 degrees, that means there's going to be 10 grams of NH3 inside. This is the max that will fit. Can you see that? That's the max. That means this solution is fully saturated. If you try to put even a little bit more in, it wouldn't go in. It would fall out of solution. When a solution is saturated, it's literally holding the most stuff that it can, like my chocolate milk. Any more chocolate, the chocolate sauce falls to the bottom. It can't dissolve anymore. Every single curve on table G, every point of every curve, that's the most amount of stuff that can fit into 100 mLs of water at that temperature. You can never be above the curve. Nothing on this table ever supersaturates. You could be below the curve, right? If you only have 5 grams of ammonia in 100 mLs of water at 90 degrees, well, there's room for more. You can get up to 10. So if you had 5, you could be under the curve. You could be unsaturated. At 10, at 90 degrees, you'd be saturated. If you put more in, you'd be saturated and then some would fall out, right? Let's see how this math problem is done. How many grams of ammonia fits into a smaller solution? This graph is about 100 mLs. What if, well, you could have a smaller solution, right? Look, I'm going to draw it. Here's a little picture. Look, we got a little solution right here, a little solution. You could have a little solution. It could be 90 degrees. It could be saturated with ammonia. We're going to have to copy this. Now, let's go really slow. I'm going to show this to you. The first thing we do is we write 90 degrees, so we pay attention. We know what we're doing on the graph. Then we're going to write down what are we looking at. In this problem, we're looking at ammonia dissolving into water. So we put ammonia over water. We're going to set up this ratio so that all the numbers on the top are the ammonia numbers and all the numbers on the bottom of the water. Now, according to table G, at 90 degrees, 10 grams of ammonia fits into 100 mLs of water. Look, right here. This point right here, it tells us that. Now, I didn't put an equal sign in here. Let me see if I can throw an equal sign in. I'll do some quick drawing here because I actually probably should have an equal sign, right? This is going to be an equal proportion. 10 grams of ammonia fits in 100 mLs of water. The question is, how many grams will fit in just 50 mLs? Well, 10 fits in 100. That's the truth. That's maximum saturation. But what if we had a smaller solution? You probably do it in your head, right? But this is how you do it. You cross multiply, 100x equals 500, and then you divide x equals 5 grams. And that makes sense. If you have a 100 ml solution, 10 grams fits in. If you have half of that, well, you have half as much ammonia fits in. So that's how that works. We can do this over and over with all different kinds of things. Now, let's see. How many grams of KCl fits into 100 mLs of water at 10 degrees? Let's find this. We got KCl and 10. That's going to be 30 grams. Make sure you get your finger on that. But what if we have a really big solution? 30 grams fits into a 100 ml solution. But what if we got a bigger solution? Well, the same amount fits in by proportion, so we have to figure out how to do that. So to do this, we write 10 degrees because we got to know where we're starting. We write KCl over water because we don't want to get confused. There's 9 other lines and we don't want to look at the wrong ones. And we just figured it out. There's 30 grams of potassium chloride fits in a 100 ml solution. Now, of course, again, I probably should have my little equal sign here because it's a proportion. Hard to make these slideshows perfect. If it was a regular class, I'd have a white screen and I'd write this on the board with the marker. I'd get the equal signs. I guess I forgot them. So if 30 grams of potassium chloride fits in 100 mLs of water, how many grams fits in a 350 ml solution? It's a perfect proportion, except now it's bigger. How do you do? You cross multiply and divide. 100x equals 30 times 350. If you do 30 times 350 here, I'll do it for you. Make sure you know how to do this stuff, all right? 30 times 350 equals, can you see this? I don't know how to make this look better. That's the right answer. 10,500. So 105 grams of KCl fits into this bigger solution. Every single time you look at table G, you're going to get the perfect measurement for one size solution, 100 mLs. You can make them smaller or bigger by proportion, cross multiply and divide. You can have 30 grams of this in 100 mLs of solution, right? You can have an ocean full. You just got to know how many mLs it is. You could do the mathematics to figure out what does this proportion equal at a bigger solution or a smaller solution. How many grams of ammonia fit into 100 mLs of water at 10 degrees? Well, we got to get the table out. Ammonia line at 10 degrees, it clearly shows 70 grams. Make sure you get the finger on that. And I know it's ammonia because down here it says ammonia and I just followed it back. So 70 grams of, let me show you how to do this, right? 10 degrees, NH3 into water, and we get 70 grams in 100 mLs. That's our starting point, right? That's where we're going to start. We only have 12 mLs in this crazy little solution, 12.0 mLs x grams. Here's the math setup. Every single time, even if you're smart, you write the temperature, you write what you're looking at. In this case, we're looking at ammonia in water. And at 10 degrees, 70 grams of ammonia fits into 100 mLs of water. That's perfect. That's saturated. Well, if 70 grams fits in 100 mLs, how many grams fits in 12? You got to cross multiply. I missed my equal sign again. I'm like the equal sign fool today. I haven't gotten a single one. Look at that. I think I missed them all for some reason. There we go. Cross multiply and divide. 100x equals 70 times 12. 84, 840, and then you divide both sides by 100. So in a much smaller solution, you have a much less. But you know what? Even though it's a little baby 12 ml solution, it's still saturated because 70 grams fits in 100 mLs, and by proportion, there'd be 8.4 grams in just 12 mLs. And this happens only at 10 degrees. At different temperatures, it's a different number. You got to use table G to your advantage. All right? Oh, look, that equal sign. We'll see it carried over. We'll see if it works. I don't know. How many grams of KClO3 fits into 844 mLs of water at 373 Kelvin? Now, holy cow, there's a lot going on in this question. All of a sudden, it's a little different, but it's not. Let's go slow. KClO3. There it is. There it is. 844 mLs. That's a big solution. We only know about 100. And what the heck is 373 Kelvin? What are we doing here? It's 100 degrees centigrade. Don't get all upset. So at 100 degrees centigrade, the KClO3 line is 60 grams. You see it? I don't know how to do this. I need a camera person. 60 grams. So let's do the setup. Ready? My equal sign's in the wrong place now. Before I didn't have it. Now that I got it, it's in a different place. Here we go. There's the equal sign. If we looked at KCl3 in 100-degree water, 60 grams of this stuff fits into 100 mLs. How many grams fits into 844 mLs? Well, I don't know. It's a proportion. You got to do the math. 60 grams fits into 100 mLs. I don't know how many grams fits in 844 mLs. We do the math. Cross multiply. 100x equals 60 times 844. That means 100x equals 50,640. Divide both sides by 100, and x alone equals 506 grams. So that means if 60 grams fits in a little solution, more grams fits in a much bigger solution, right? More grams. In this case, we did the math, 506. Easy peasy. I'm telling you, this is easy. Here, let me see if I can clear all drawings. I did it. They're all gone now. I'm not going to have an equal sign on the next one. Same question, but I'm asking it different. I got to move my picture out of the corner so I can't see what's behind it. Let me make sure I can read this. How many grams of sodium nitrate will it take to saturate 64 mLs of water at 283 Kelvin? What's up with this Kelvin? Pain in the neck, right? 283 Kelvin, that means 10 degrees centigrade. If you don't believe me, do the math. K equals C plus 273. So we have 10 degrees. We need sodium nitrate. So where's the sodium nitrate line? Sodium nitrate's way up here. 10 degrees, it looks like 80 grams of this stuff fits into 100 mLs of water. So let's see, how would we do that? I would do it this way. At 10 degrees, we have NaNO3 into water, and it would be 80 grams fits in 100 mLs, and that's going to equal to X grams in 64.0 mLs. Look how easy the setup is, right? We write the temperature, we write what we're looking at, sodium nitrate in water, and the table tells us 80 grams fits into 100 mLs, so how many grams fits in 64 mLs? Cross multiply. I don't have my equal sign again, oh my gosh. 100x is gonna equal 80 times 64, that's 5,120. So 51.2 grams of NaNO3 fits into this smaller solution. This again, I'm telling you, is not hard. Table G gives us the perfect starting point. Hardly any solutions are 100 mLs, right? They're always a little less or a little more, a lot less, a lot more. It's all a proportion. It's perfect. Table G is perfect, and then we make a proportion. Cross multiplying divides baby stuff, all right? That's 4th grade, 5th grade math. Right? Maybe 3rd grade or 2nd grade in Vestal because you kids are better than normal. All right. Why does New York State put 10 curves on table G, right? Because they hate your guts and they don't want you to get 100 on the regions. They want you to get nervous. They want you to get confused. Don't worry. Don't worry. Should you ever get confused or let it bother you? No. They stink. They're stupid. You're smart. 100 mLs of water is the same as 100 grams. That's another dumb thing they do. 100-gram solution. Who talks like that? 100 mLs. Now, the density of pure water, 1.00 grams per centimeter cubed, or the same thing, 1.00 grams per ml. Grams of water is grams of water. Centimeter cubed and mLs is the same value in volume. A centimeter cubed is an ml. Usually we use mLs for liquid, but it doesn't matter, right? And usually we use centimeters cubed for solid, but it doesn't matter. A centimeter cubed equals a milliliter. Do other elements or substances have this 1 gram equals 1 ml or 1 gram equals a centimeter cubed? No, they don't have the same density. The density of water is 1 gram per ml, and that's equal to 1 gram per centimeter cubed because a centimeter cubed and an ml are the same. No other elements, no other compounds that I know of have exactly the density of 1.0. Why not? Because they have different densities. What's so special about table G? It's a little tricky, but we're smart. We own this. We own this like a dog on a leash. You could put this on a leash. You could call your dog table G. You could say, G, fetch. G, sit. You could own this table. Don't you worry. Isn't chem fun? This is easy, right? Why does this work? Hydrogen bonding. That's always the answer. All right, I think this is the last one. Yep. Look at that picture. That's what's coming, but we're not going to look at it now. Ready? Peace, love, and chemistry, and water.